Greetings and salutations. Welcome to Mechasoftronics Workbench. Most of my videos will be for those folks that are upcoming electronic enthusiasts and may not have experience with some types of test equipment and basic electronic design outside of higher education communities. The black box you're seeing on the bench is what is called a dim bulb tester, or in electronics parlance, a DBT. This is a piece of equipment that I finished putting together a few weeks back, which I will be using to test mains power equipment that I will be repairing. When working on high voltage equipment that you do not have a history of, it is best to use a dim bulb tester system, okay, instead of plugging the equipment directly into a wall socket and switching it on. So bad things can happen with a piece of equipment you don't know the history of. So when I say a system, what is included in that system are an isolation transformer, a variac, which then feeds power into the dim bulb tester. I'll touch only briefly in this video on why to use an isolation transformer and a variac. There are many videos on YouTube that explain both of these pieces of test gear, how to set them up correctly, and how they're used. So, what does a dim bulb tester do, you ask? A dim bulb tester somewhat limits the current that's being applied to your device under test, or if you like, a buffering action takes place via the resistive filaments in the light bulbs. It does this by passing the load current through incandescent light bulbs. You cannot use LEDs for this purpose. Their resistance is not the same as a tungsten filament light bulb. So, incandescent light bulbs, as I just mentioned, use tungsten filaments to create light, and to do this, the filament must have resistance. It is this resistance that we are using to absorb any high currents that may be caused by shorts or bad components within the equipment that you're testing or repairing. If the device under test draws excessive current, the bulb lights brightly and limits current, protecting the device under test and the circuit. If the DUT draws normal current, the bulb will glow dimly or barely at all. So as you can see, we're looking at the front of the dim bulb tester on the bench here. And I will turn this over and talk to you about how we're applying power into, out of this box. So I had been delaying in building this device as I was not sure how I wanted to mount the various components and onto what base or base material, or into what type of chassis. I kind of knew what I wanted to include in the build of this piece of equipment, but mounting some of this onto just like a wooden board or a piece of phenolic, etc., where everything is open and exposed, I wasn't too happy in doing. However, I was fortunate enough to come across a rather nice plastic box, which was large enough and deep enough to house all of the controls, etc., that I wanted to include. So first of all, let me show you the back of the device so that you can have a mental picture of what is being controlled via the front of the device. So as you can see, I've got these inputs and outputs labeled. And so on this side here, we have our mains power in, so this is coming from the wall socket. And the hot or line in from this connector then goes directly to this 10 amp breaker. Now, some people may comment or ask, why am I using such a high current breaker for this device when most, especially tube electronic equipment, will work anywhere between, or draw anywhere between about 1 to 5 amps. So I will be working on power amplifiers, etc., that can draw considerably more than 1 to 5 amps. And so I've built this system to be able to supply a constant 8 amps of current to any load that I have on the device. For instance, I built a linear power supply for my ham radio, and it is 110 volts in, or 124 is about what our voltage is here, line voltage. And it puts out 13.5 volts, but the current can be over 30 amps on that 13.5 volts. So the input current can go as high as 7 amps, especially on first turn on, even though there's a, let's say, a snubber circuit or a resistive device in series with the primary of the transformers to limit inrush current. Anyway, so moving along. So we have the mains power connector. We have the 10 amp circuit breaker. From this 10 amp circuit breaker, it then goes to the power switch on the front of this device. And from the power switch, it then comes to this line out duplex connector. So this is line out voltage. It is not filtered, it is raw. So in other words, it's not going through the isolation transformer or whatever. So I can power my isolation transformer and variac from this, and then I can also power another piece of equipment that does not need isolation from this also. So then you say, well, we have an isolated input. What does this mean? So the isolated input is what's coming back from the isolation transformer and the variac. So we have a series circuit here. The line comes in, goes through the system, comes out the line out. The variac plugs into the line out. Sorry, the isolation transformer plugs into the line out, and the variac plugs into the isolation transformer. Then the variac, boy, getting this good. The variac then comes back and plugs back into the isolated in. So let me say this again. So we have the line in coming in here. The hot's going to the 10 amp breaker, goes up through the switch on the front of the DBT. From there, it then comes back out line out. So this is still mains voltage coming out of here. The isolation transformer plugs into here, and then the variac plugs into the isolation transformer, and the output of the variac then plugs back into the isolated in here. So now we have isolated 110 volts or 120 volts. We have isolated 120 volts, and we have variable AC. So isolated variable AC coming back in and feeding the dim bulb tester. Okay, so let's turn this over and we will talk about the front of this device. So here's the front. So starting on the top left, up here we have an LCD display. This actually shows considerably more than what I actually need. This particular display, I picked up 2 of these a while back off of Amazon, and they were in my parts box and I needed a use for them, so I put one here on the DBT, and I also mounted one into the front of the isolation transformer. So really the only thing I'm using off of this particular LCD is I'm measuring the amount of current being drawn by the load when plugged into the dim bulb output duplex here. And we'll show that to you later on. So here's our main power switch. off position, on position, and we have a large 10 millimeter LED that is green, so that when power's on, that will shine green. Up on the top right side here, we have two bulb sockets. One is marked as low, one is marked as high. That is our bulb resistance. So these are E11 bulbs. And the reason I selected E11 bulbs, which are little tiny guys like this, is that I didn't want to mount large incandescent bulbs up here on the top. And I was fortunate enough when searching on Amazon that I ran across not only these E11 bulbs, but I also ran across these ceramic chassis mounted sockets. So it was very fortuitous to find these on Amazon. So the 50-watt bulb, this is a 50-watt bulb. You might be able to read that right there. This 50-watt bulb is the high resistance bulb. And so we're going to screw that into there. And the lower resistance bulb, which will basically be 1/2 of the 50 ohm bulb, is the 100-watt bulb. I don't know if you can read that there. And we'll put that into low resistance. So for those young folks that are just learning all about this, power, watts in other words, to find out what the hot resistance is. In other words, when this bulb is glowing full brightness at 124 volts, what is the resistance of that filament? So Ohm's law, V squared divided by power, or watts, okay? And that will give you, a mathematically correct filament resistance. In real life, it's going to be a little different, as you probably already know. So you can measure the resistance of these bulbs with an ohm meter or a multimeter on ohms, and you'll get a very low resistance. I think the 100-watt is 10 ohms when cold. I think that was the 100-watt, was 10 ohms when cold. But it's pretty high. So let me take my little calculator right here. And if we take 124 and we square that, and we divide that by 100, so we're going to get 153. So 154 ohms, presumably, when that bulb is lit, fully lit. So when you plug a device in that is under test, and you have the bulbs switched into the circuit, this becomes somewhat of a buffer. The bulb that is selected is somewhat of a buffer. So if you plug in and you turn on and you start turning up the power or the voltage via your variac, and the bulb starts to light really, really bright, then you know you are having too much current draw from your device under test. So that's a real quick explanation of what's going on there. So, however, let's get back to what the switches do. So I've put the two bulbs in, and I can select those bulbs, high resistance or low resistance. Now, this switch here is very important. So we have it currently set for bulb, which means that one of these bulbs, the selected bulb, is in series with your load that is plugged into the dim bulb outlet. If you put it to bypass, you're bypassing the bulbs and you're getting full selected voltage from your variac to your device under test. So you want to be very careful when you have this in bypass, because even if you have only, let's say, 10 or 20 volts selected on your variac, if you have a short circuit or something that is got a very low resistance, it's damaged, for instance, a very old capacitor in a piece of equipment, you start drawing a lot of current. So even at low voltage, you can draw very high currents. Okay, so you want to make sure that you are setting this up before you turn on any power to this, that you're setting it up in a specific configuration. Let's look at that configuration. So main power is off. We would have this switch in bulb, and we would have this on high resistance. So this would be your startup before you turn on your mains power or plug in your device under test. Normally your device under test would already be plugged in. Okay, so we've gone over the fundamentals of this. So let's get it set up and everything plugged into it, and then we'll have a look at the system, and then we'll see about turning this on and putting something on here that shows you how it physically works. All right, be back in one moment. I have the dim bulb tester now connected up to the Variac and to the isolation transformer. It is not turned on. We are in bulb select and we are in high resistance. So let's just go over how things are set up here. So as I mentioned earlier, the mains comes in controlled by the power switch, goes back out the duplex. The isolation transformer, which is here, is plugged into that switch duplex outlet, as I mentioned earlier. The Variac here is plugged into the isolation transformer. Please note that this duplex outlet here still has earth ground connected, which means the Variac also has earth ground connected. Mentioned earlier, there's videos on YouTube, lots of them, on how to use an isolation transformer when doing using your test equipment, especially oscilloscopes, for testing lines voltage equipment, and how Variacs work. Variac is a variable AC transformer. So the Variac plugs in to here. Now you're probably asking, okay, what's this guy for, and what is this? So this is an isolator. This removes your earth ground. This cord here is actually powering up all of my test equipment over here. I'm removing the earth ground. Okay. Now, if you're not familiar with how the earth ground and neutral in your line in or your household voltage duplex outlets work, is that at the duplex outlet, this prong is earth ground, as most of you pretty well know, and this is your neutral, the big prong. So we have a small opening, we have a large opening, and this is neutral. These two in the duplex outlet and in the box mounted in your wall are separated. They are not connected together. However, they are connected together back at your main breaker box. So your neutral and your earth ground are connected together in your breaker box. And if you do not lift this earth ground, then your isolation transformer is not really actually isolating your earth. Okay, so when you go to hook up a piece of test equipment like an oscilloscope to the device under test and you hook it to ground, you can blow the front end of your oscilloscope. Now, as I mentioned earlier, there are lots of videos on how that works. That's all I'm going to talk about on that subject here with this. So please, before you decide to do any of this, make sure you go and watch the videos on how to set all of this up. And there is a specific sequence of setup. In other words, why is the Variac not plugged in first and then vary the voltage into the isolation transformer, etc. So things like that. It's like, what is connected in series here and why is it connected in that series format? All right, so that's enough of that for now. So we have this all set up, and as I mentioned earlier, you have a before you turn it on scenario here, and a lot of equipment, especially tube equipment and tube test equipment from many years back, will generally always have a startup condition, let's call it that. In other words, switches and controls, etc., should be in a specific orientation before you apply power or before you turn the piece of equipment on. A lot of times that is in older equipment where they still had a lot of knobs and dials and switches, etc. Nowadays, everything is computer controlled. For instance, like this DC power supply here, I don't have to set anything in a specific condition. When I turn it on, the computer sets it into a specific condition. Same with the oscilloscope and the signal generators, etc. So this is for older stuff. But on this piece of equipment, because we're still dealing with switches and how they need to be set before we plug anything in and turn anything on here, it's important. So we have mains power is turned off. We have this switch in the bulb position. That's very important. And we have selected the high resistance filament bulb. Okay. The Variac transformer, we don't need to do anything with that. The isolation transformer, we don't need to do anything with that. And the Variac is set at 0 volts. Okay, so that's very important. We want to make absolutely sure that's set at 0 volts. Okay, so one other thing I did want to mention, I did show you that there was a 10 amp circuit breaker on the back of the box here. I have 2 fuses in the isolation transformer. Those 2 fuses is actually, one is on the hot and one is on the neutral. Okay, and I have 2 fuses in the Variac, one for incoming voltage, and this one here is voltage coming out. I like to protect my equipment and myself, of course, as best I can. So there was lots of room to put all of this in, and so I did put it all in. Okay, so moving along here, let's turn this guy on. Okay, so what you'll see here is, obviously I have green power LED. It's kind of not very green on the camera here, but it is quite a nice green. You might say, gee, that's pretty bright. In fact, it's not even close to being full brightness. I'm drawing very little current by these LEDs. But that's a whole nother subject that we can go into in another video on powering LEDs. So as you'll see here, the LCD has come up. We're showing 120 volts coming in on our mains. This is the mains voltage coming in. The current here is showing 0. This current is the current coming that is supplying to the load plugged into the dim bulb outlet. And we'll show this when we get some load hooked up. Now over on the isolation transformer, you'll notice that it says 124 volts and 100 milliamps. Okay, and that 124 volts is the output side, and the 100 milliamps is the output side of the isolation transformer. So because we have 120 volts here, 124 volts there, that tells me that we have maybe 1 or 2 windings or a winding and a half more on the output side of the toroid transformer than we do on the primary side, secondary side to the primary side. So as you know, or you should know, that transformers are used to change voltages up or down as necessary. And normally when you're winding a transformer, you're never going to get the windings exact. I have not calculated what that winding difference is. I don't really care at this point, as long as it's not like 140 volts or something like that. 124 volts is just fine in this particular case. So, and then we have some other stuff here. We have a power, energy, frequency, and power factors. You can see the frequency here is 60 hertz. 60 hertz. So we're drawing 100 milliamps or 0.1 amp. So what's happening there is we have a little bit of loss in the variac because it is a transformer. So we have a little bit of loss in the variac. And we're also powering a little 110 volt to 5 volt AC to DC switching converter inside here to power the LEDs. So that's what you're seeing there. You're just seeing kind of just what current's being drawn in an idle state here. This is what we call an idle state. All right. So having said all of this, let me set up some test situations here, and I'll be back in a moment to show you how this works. Okay, we are back and we have a setup here. Let me move this into view here, and we'll move this into view. Oops, let me get that to about there. I want to make sure that those don't touch, which is, it's not going to hurt anything anyway because we have it in bulb tester. So everything's turned on. I've got my meter set up here. Now, the meter is on current. It is set to amps. It's going to go into focus here. Amps, and I'm in amps. Okay. So now what we have is showing is we are currently drawing, even though we're bulb and the variac is turned to 0 volts, we're drawing 26 milliamps here. Oops, let me get my fingers out of the way. 26 milliamps here, 26, 27. We're still drawing 100 milliamps over on the isolation transformer. And you can see that we are drawing 36 milliamps through the circuit, and we haven't even turned any voltage up on the isolation transformer. That is the leakage from the variac. The variac generally never goes to absolute 0 volts. We probably have maybe a one volt or so actually coming out of the variac. We can test that later if I think about it, and we'll look at the voltage coming out when this is set at 0. So as you can see here, I have alligator clips connected to this AC line cord, and that is virtually a dead short across here, and a dead short across here, and the reason is because it's on amps on the meter. Okay, so make sure you're very careful when working with this kind of setup, as that is indeed a direct short. Okay, so when we start turning up the voltage, what we're going to see is the current is going to rise here, 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 and here. I keep putting my hand in the way, it goes out of focus. But we're in the bulb setup. So what's going to happen is the bulb is actually going to start glowing. And as I turn the voltage up more and more, this is going to glow more and more brightly. And this is how this is going to react with your device under test. So if your device under test has a short or a bad capacitor and starting to draw a lot of current, this bulb is going to light up very brightly as you increase the variac voltage. And this is your telltale sign that there's something wrong with your device under test. Okay, and then I'll show you later, we'll hook up a light bulb. I think it's an LED light bulb I have, and we'll plug it in, and we'll show you that it's kind of simulates the filaments of a tube device, and you'll see that the bulb will light up very, very low, even though the light bulb is actually lit up and running just like a regular light bulb. Okay, enough explanation of that. We'll show you that in a few moments. So as I start to turn up the voltage, you can see that the current immediately came up. Okay. Also note, boy, that you can barely see it, but the bulb has started glowing at 186 milliamps. So as we're turning this up and we're getting more and more voltage applied, of course, we're getting more current flowing through. And this is where we can actually measure what that hot filament resistance is by doing this action here. I would suggest you just use Ohm's law and calculate it like I mentioned before, V squared divided by the power, or watts. And we can do that calculation. I can't remember what the value was. Well, that was on the 100 watt bulb. This is on the 50 watt bulb. So we'll have to recalculate it. But we'll look. We'll see what the difference is from the calculation to what we're actually seeing. And this meter is pretty accurate. So yeah, it'll be an interesting calculation. So here we're at about 70 volts. My Variac here is actually pretty accurate. It does slide off a little as we go up by a couple of volts, but it's pretty accurate. And so as I'm turning this up, you can see that bulb is getting really bright. So now we're all the way up to 125 volts. We're doing 125 volts output. You can't see it because this is blocking it, but there's 125 volts showing and 524 milliamps, or a half an amp, okay, is being drawn. So down here, you're going to see it says 0.422 or 0.423. So remember now that these are 100 milliamps difference. If you remember, that was already showing 100 milliamps. So you subtract 100 milliamps and you get 423 here. Note that we have 410 milliamps or 0.4 amps on the bulb. That's how much current the bulb is consuming, how much power the bulb is consuming at this time. Let me turn this down. So 400, let me do this, 410. Let's say 410. So we'll turn that back down and we'll go 410. So what did I say? 124 squared divided by, in this particular case, 50. So that resistance is 307 ohms. Okay, so 124 divided by 307. Well, come on, 307. 403, 404 milliamps. So very, very close. You can see that measuring that current, the bulb, and the math, when we just said 124 volts at 50 watts, what would the current consumption be? 404 milliamps. So we were very, very close, okay, on what it was. So just thought I'd point that out. Okay, so that's how the dim bulb tester works. There is no way that you can be running a test like this and then switch this to bypass. You will blow the fuse either in your multimeter, which you probably will, or you're going to blow one of the other fuses or the breaker. Okay, so this is why you want to make sure that you always have this in the bulb side when you're running any of your equipment that is connected to this, until you're absolutely sure that you have no issues with your device under test. All right, so let me stop this here for now, and I'll plug in that light bulb, and we'll have a look at that and see simulate what a real piece of equipment would be doing, or causing this to light up like and show the current draw, etc., in a pseudo real life scenario. All right, I'll be back in one moment. Okay, we're back with a simulated load that we'd be testing. That load is going to be this 25-watt incandescent bulb, and we have it connected into our output. So here's something that I didn't mention earlier, and I thought about this when I was plugging this in. This particular cord is a two-prong cord. It does not have an earth-ground connection. If your piece of equipment that you're going to be testing has only a two-prong cord, your earth ground is disconnected. So you still do have to be careful when connecting an oscilloscope, etc., to your piece of equipment that you're testing, in that you're still getting an earth ground connection. If you don't have your oscilloscope isolated off of earth ground, you're still going to get an earth ground to neutral connection. So be careful on that. In this particular case, I have no earth ground connection here anyway. It's a plastic box. Okay, so something to note if you're building this into a metal box, and a lot of folks will put them into a 4x4 metal box with a metal lid, and they may earth ground that metal box for safety. The problem is that all the duplex outlets that I've worked with, the earth ground connection here is actually connected internally to the mounting tabs on the duplex outlet. So if it's in a metal box and you've earth grounded the metal box, you're still getting an earth ground here. Okay? Even though you're coming through your isolation transformer, you're still getting an earth ground. That's when you need to make absolutely sure that the earth ground on your variac or on your isolation transformer is lifted on these outputs. In other words, you've got an isolator like this guy here. I'm trying to get this to focus, like this guy here. So just a quick note. Again, I want to make absolutely sure that you go and look at isolation transformers and variacs on YouTube if you're not familiar with how these setups work. Lots of good information there on how to set this up and how these can be set up by lifting earth ground. Okay. So, right. So we have main power turned off. We have it in bulb. We have it in high resistance. And we have a 25-watt bulb here that we're going to use as a load. Let's say we're powering up the filaments in a old piece of test gear. And I mention that because I have a piece of test equipment that was made back in the early 1950s and used on Navy ships for repairing radio equipment while a ship was at sea. It's a signal generator, an RF signal generator. Very interesting piece of equipment. The build quality is impressive. It literally is built like a tank. Anyway, that's a future video that we'll look at with that, and we'll be using the dim bulb tester to apply power to it when I first turn it on. I have not plugged it in. I haven't turned it on. I haven't really done anything with it. So it'll be interesting to see how it works. Anyway, so getting back to this. So I have my variac turned to 0 volts. I'm in bulb mode. I am high resistance. Power is turned off. So let's turn the power on. Let everything settle. Okay. So I'm not sure if this is actually switched on the back. So let's see if we can apply some power here. Yeah, no, it's not turned on. So let's see if we can see if that does it. So as I turn this up, yeah. So as I turn the voltage up, I'm at about 40 volts right there, AC, 40 volts AC. Over here, we're drawing 147, 148 milliamps, feeding the system. Our current going to the bulb is 113 milliamps, or 0.112 amps at 40 volts. So this is like we're applying power to that piece of test equipment I just mentioned earlier, and the bulbs are just kind of starting to heat up. So if we look at this and this as the filaments in that piece of equipment, notice that, let's say, the filaments of this tube are lighting up, okay? But notice that the bulb is not lighting up. So the current draw, in other words, our device under test, is not drawing any excessive current to cause this to start to light up. As we turn up the voltage, this will start to light, but it won't go super bright. So let's go up a little higher here. The bulb here, you can just barely see it. It's actually just starting to light now. Okay, so as I turn this up all the way, so we are now at 124 volts. I know this says 130 plus, but it's actually 124 volts. You'll notice that this is very dim, but this is really bright. So that tells me that my piece of equipment, this being the piece of equipment, is operating correctly in the way of its current draw. When I say operating correctly, I mean that its current draw is not excessive. It's not telling me that I have a short circuit or something in the device that's causing a lot of current draw. If I flip this over to the low side, you'll notice that that went considerably more bright, and the filament here is basically off. I can't even see any glow on the filament here at all. And that's because it's passing pretty well all the current into our device under test. Okay. Now, let's say this is my device under test, which it is in this particular case. And I go, okay, well, it looks like everything is fine. We can actually switch this over to bypass and we'll get full voltage to our device under test. So I can go over to bypass. You notice I have this as a red LED. That's telling me danger, danger. Don't keep it in that. If I turn this on and this is lit up and I start turning up voltage, I want to make sure I see that that's red and I'm in the wrong configuration on first startup, as we talked about earlier. So when I change this out, I'm not sure if you're going to see this or not. Maybe I can hide that a little bit. Yeah, you can't really see it. So the change in current is minute. So we have 216 milliamps here when in bypass, so that's full voltage going to our device under test. And when I switch it out, go to bulb, this drops to 212 milliamps. Very, very small change in current. So let's go over to the high resistance side, and you'll see that this is 191 milliamps now being fed to the device under test. So now this is where you're going to really see the difference. If I go to bypass, you'll notice that this now goes back up to 216. So that shows you that the bulb here is buffering the current or limiting, soaking up some of that current that your device under test is drawing. And that's basically the fundamentals of this whole system. So I will turn this back down to 0. That's all good. Everything is fine here, and I will turn that off. And basically at this point, we are done with this video. And as I mentioned earlier, the next video I do will probably be the one where we hook up that signal generator and start to have a look at it. All right. Well, thanks for joining me in looking at what a dim bulb tester is and the system that is involved in setting up for testing line voltage equipment. And we shall see you next time.